Last time we have derived the del operators in spherical coordinates. This time we shall do the same for angular momentum using these results. Let's start with the Cartesian coordinates representation in the yellow box. We begin with the simplest case, the rotation about the z-axis. In spherical coordinates, the rotation about this axis is just the change of only the angle phi. For an infinitesimal rotation, this is given by this change of the function psi can be written in the form below, where L3 is defined as the following differential operator. This is its representation in spherical coordinates. Let's do this more carefully. What we can be certain is that L3 is proportional to the derivative with respect to phi. We shall work out the rest by using the spherical representations of del 1 and 2 and verify the relation in the green box. Taking the red box into considerations means we can drop the derivatives with respect to the other coordinates. This is a great simplification. Let's plug all these back into the expression above. Notice that the terms r sin theta cancels in the product between x1 and del 2. A similar cancellation occurs for x2 and del 1. Therefore, we shall ignore r sin theta. This gives for x1 and del 2 just the square of cosine phi. Similarly for x2 del 1. This matches our initial calculations. Thus we have L3 in spherical coordinates. Let's proceed with the rest of the components. Let's write L2 in a form that is more easily compared with L1. L2 is transformed into L1 by the same transformation that converts x1 to x2, which we have introduced in lecture 8, with an additional minus sign to be included in the end. By these conversion rules, we only need to solve for L2 to get L1 for free. Since the angular momentum operator must depend only on angular variables, as it is the generator of rotations, we can drop all derivatives with respect to r. This is correct, even though L2 also seems to depend on the r coordinate through x1 and x3, because they occur after the differential operators and therefore are not affected. Let's substitute all these back into L2. For x1 del 3, we have for x3 del 1, combining these two results, we now have L2. Let's perform the transformations that will give us L1 from L2. Thus, without having to do much work, we have derived the spherical representation of angular momentum. We now wish to do the same for L square, so that we may solve for its eigenstates. First, notice that all the components below, when squared, have the following constant prefactor. These are of the same value for all components. It would therefore be convenient to first factor them out and plug them back in again at the end of our calculations, so that we don't have to carry around all these constants. Therefore, the square of L3 will be equivalent to this. How about the sum of the squares of the remaining two components? Here, we can again use the relation between L2 and L1, which we have just seen. The square of L2 is given by the remaining term is just the square of L1 related by the transformation. This transformation has the following consequences on trigonometric functions, which we have used previously. To make it easier to apply these relations to the expression below, which consists of products of trigonometric functions, we derive some useful combinations of the transformations in the green box in the two red boxes. To make it even more convenient, we further modify them in order to directly include the terms in the second blue box below, such that by just transforming the first blue box, we get the result of the full sum. Let's take the first transformation as an example. We can map the original term, the square of sine phi, into the sum of itself with its transform. The result is obviously 1. Such a transformation on the first term below will automatically include the second, so we may drop it. Let's do this for the rest of the transformations. This new green box is what we will be applying to the blue box. In the end, we expect to get the sum of the squares of L2 and L1. Let's first expand the product of these two brackets. This is the first calculation we are actually doing after using all our tricks, so pay close attention. Let's do this systematically and first look at the product of the first term in the leading bracket with the second bracket. Look closely at the terms cosine phi and sine phi. Sine phi can be moved right next to cosine phi, bypassing the derivative with respect to theta. By the last transformation in the green box, this product is 0. So we only have the two remaining terms. We can then apply the second transformation in the green box to the blue box, which is just 1. Let's look at the product in the blue boxes. First note that the derivative theta can be moved all the way to the back, next to the cotangent. We can then concentrate on the red box, which consists of only functions of phi. This is a simple derivative. Expanding this out, we get the following differential operator. Applying the transformations in the green box, we have we can move this function of theta past the derivative phi. Let's expand this term in the blue box, which is very similar to what we have just done. After applying the green box to this, we are left with just the double derivative of phi. There's an additional step we would like to do that would tidy things up a bit. Let's see if we could combine terms like the ones in the blue box into a single term. Since this has two derivatives of theta and has in the cotangent a sine theta, we may try something like this, which gives... This is already looking like the blue box. Dividing by sine theta will do the trick. We are now ready to add in the square of L straight. Applying some basic trigonometric identities to this. And we finally have the representation of L squared in spherical coordinates. But let's not forget the units carried in the prefactor, which we have factored out in the beginning. This completes our calculation of L squared. There's an alternative way of expressing L squared in position space that will be useful for solving its eigenfunctions. We shall do this in the next lecture.